Welcome to Physical Sciences Consultorium. This video is part of the series How We Know the Universe. In this episode, we examine how cosmological models are tested, not by belief, but by predictions. Cosmology studies the universe as a whole. We cannot experiment on it. We cannot rewind it. We cannot create a second universe for comparison. Models are the only way to connect physical laws to what we observe. A cosmological model is not a picture of the universe. It is a structured framework built from physical assumptions and equations. Its value lies in what it predicts, not in how intuitive it feels. A model that cannot be tested is not scientifically useful. A valid model must make predictions that could turn out to be wrong. Risk is essential. In cosmology, predictions are rarely about single events. They are about patterns, distributions, and relationships. Models predict how quantities change, how structures are arranged, how signals should appear. Predictions are made before data is examined in detail. This prevents models from being adjusted to fit observations after the fact. Prediction first, comparison later. Cosmological models predict how the universe expands over time. Different assumptions lead to different expansion histories. Observations test whether those predictions match reality. Models predict properties of background radiation, its uniformity, its fluctuations, their statistical patterns. These predictions can be checked independently by different experiments. Models also predict how matter should cluster over cosmic time. They specify sizes of structures, their distribution, their evolution. Observations either support or constrain these predictions. No single prediction is decisive. A model might succeed in one domain and fail in another. Reliability comes from multiple successful predictions, not isolated agreement. Predictions are tested against independent observations. Different instruments, wavelengths, and techniques probe different aspects of the same model. Consistency across datasets is a strong test. Predictions are not compared to exact numbers. They are compared within uncertainty ranges. Agreement means predicted behavior falls within observational bounds. If predictions consistently fall outside uncertainty ranges, the model is challenged. Small mismatches may be tolerated. Persistent failures are not. Models can sometimes be refined, but adjustments must be physically motivated and must improve agreement across all tests, not just one. Endless adjustment signals a deeper problem. Model failure is not wasted effort. It reveals which assumptions do not hold and which directions are promising. Progress comes from elimination, not accumulation. As data improves, predictions become more tightly constrained. A model that once worked may later be ruled out. This is expected. Cosmology does not ask whether a model is true. It asks, which model explains more observations with fewer assumptions? Success is comparative, not absolute. Consensus does not mean certainty. It means that one model currently outperforms alternatives across available tests. Consensus is provisional. Speculative ideas are constrained by the requirement to produce testable predictions. Without predictions, ideas remain outside scientific cosmology. Cosmological models are tested by the predictions they make and the observations they survive. They stand not by persuasion, but by consistency with evidence. Cosmology advances not by proving models correct, but by ruling out those that fail. If this way of understanding space science is useful to you, this is exactly what Physical Sciences Consultorium exists for. We focus on how scientific knowledge is built. If you found this episode helpful, please like, share, and subscribe to the PSC channel.